Hello, everyone, and welcome to Office Hours with the Meter Environment team. Today's session will focus on CDX technology, and we're shooting for about 30 to 40 minutes of Q&A with our experts Leo Rivera and Chris Chambers, whom I will introduce in just a moment. But before we start, we have one housekeeping item. If you're watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your question on our website at metergroup.com. And then someone from our science and support team will get back to you with an answer via email. All right, with all of that out of the way, let's get started. Today, our panelists are application specialists Leo Rivera and Chris Chambers. Leo is a research scientist and director of science engagement at Meter Group. He earned his bachelor's and master's degrees in soil science at Texas A&M University, where he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Leo is the force behind application development in Meter's soil hydrology instrumentation, including the Satro, HyProp, and WP4C. He also works in R&D to explore new instrumentation for field measurements of water content, water potential, and hydraulic properties of soil. Chris Chambers is a product scientist at Meter Group. He draws on over 15 years of experience as a support scientist and his background in ecology and plant physiology to improve Meter's instruments and to help Meter's clients collect the data they need to test hypotheses and make management decisions. Thanks for joining us, guys.
Happy to be here.
Yep, always excited.
It's been a while since we've done this, Leo.
All right, let's get started taking questions. And again, today we're going to be hitting the topic of CDX. So basically, just right off the bat, can you guys tell us what is CDX?
Yeah. Well, I'll start off. So CDX, which stands for Complex Dielectric Through Intersections, is a new technology platform for measuring soil moisture, and more specifically for measuring dielectric permittivity. And I think it's pretty exciting new technology that we've been working on coming out with.
One might ask, all right, another sensor, really, guys? But not to take anything away from the Teros line, there's a reason why we invested so much effort with the sensor, and we're happy to talk about it some more.
Yeah.
So this first question here, in general then, how is CDX different from, I guess, your standard soil moisture sensing?
I think we should start with the complex dielectric part. And this ties directly into an area of math called complex numbers, about which Leo is going to give us all a primer right now.
Thanks, Chambers. Yeah. So, I mean, ultimately what we're trying to do is separate the imaginary and the real portion of dielectric permittivity. And what we're doing that is through some pretty cool complex math where we're essentially taking these measurements and using geometry to solve where these voltage ratio measurements create these circles to intersect, which actually aligns with our imaginary and real portion of the dielectric of whatever media it is that we're measuring. Of course, we're typically focused on soils, but that's what we're trying to do. And so that's kind of where it comes in. But ultimately, it's how we separate out those components.
And the key term there is intersections.
Yeah.
And that's where the math problem becomes a geometry problem. And a diagram would be great right here, but we're going to refer you to our website and the instrument manual that have an actual diagram of the transmittance plane. But the real key here is the complex dielectric, which has two components, the real dielectric and the imaginary dielectric.
Yep.
And the trick is that since we've made it a geometry problem, those two components are basically two vector components of the complex dielectric. And that's how we get at both of those.
Yeah.
Ba-doom-cha.
Nice. And if you think about traditional soil moisture sensing technology, I think the important point to understand is that those are primarily measuring, typically looking at apparent dielectric permittivity. Mm-hmm. And that's an important thing as we get further down the road to understand why we need to separate those things out. And why we can sometimes be limited by measuring apparent dielectric permittivity. It's not to say that these traditional technology are bad, because in the majority of situations, they measure really well. It's when we get into those edge cases in those more complex environments that have more challenging things like salinity that we see the traditional technology tends to not do as well. And that's where our efforts, where we're continuing to try and improve our measurement tech, always trying to find better ways to make measurements, has helped solve some of those pain points.
But whether it's like a Teros, which is a capacitance sensor and is actually measuring the relative charge time of a capacitor, or a TDR probe, which is actually measuring the time that it takes for an electric wave to propagate back, the complex dielectric sensor is actually measuring the real and imaginary dielectric.
Yep.
Okay, what do you mean then by measuring the real and imaginary parts of dielectric permittivity?
Mind if I take a stab at this?
Go ahead.
You can go ahead.
No, go for it.
After you.
No, you first, Chambers.
All right. So the two components of this, there's actually, the way that I like to think of it is that the real portion of the dielectric is very much analogous to the capacitance, the storage in the system. And the imaginary dielectric is more related to the lossy part of the system, where you get conductivity out of the system. So you've got your real, which is, basically an electric charge being stored in your soil. And then the imaginary is leakage from that storage. And with those two components, then we get dielectric permittivity, the real dielectric, which relates to the water content the most, and the electrical conductivity relates more to the imaginary dielectric.
Yeah. No, I think that's the exact right way to put it. I mean, ultimately, we're interested in typically the water in the soil, which is primarily the real dielectric permittivity. Of course, we have other components that are part of the mixing model with the soil and air and things like that. But then you have those lossy parts like the solutes and the lossy clays that can cause essentially add to that essentially add to that and can cause our readings to go up if we're not actually separating that out. And ultimately what we're trying to get to is the amount of water in the soil and separate out those pieces.
Okay, with everything that you've just said about the real and imaginary parts of dielectric permittivity, why does measuring real dielectric permittivity improve soil moisture readings then?
I think ultimately it's because like we've said, our ultimate goal is to measure the amount of water in soil. And if we can separate out those things that can affect that measurement, like solutes, it makes for a better measurement. Now, beyond the fact that we can do a better job of separating out those things, we've also done a better job of improving the measurement circuitry itself, which ultimately is also leading to a better water content measurement where we can make more consistent sensors across batch to batch in time. But we can directly reference those sensors against primary standards as well.
And I'm going to introduce a little bit of nuance to this because no matter what you're doing when you're using an electrical property to measure water content, so much depends on the calibration for the accuracy. And if you look through different water content sensors, you'll see kind of a divergence in the accuracy. And a lot of that is plus or minus 2 to 3% of the real water content. So you can, like in the case of the Teros, it still gets at a very good water content, even though it's measuring apparent dielectric. But where the real trick is that the calibration for the Solix 14 is much more mechanistic than the Teros 12. Correct me if I'm wrong on that.
Yeah, I think that's a great way to look at it. Yeah. And so ultimately it's just, about separating out those things that impact our measurement and continuing to improve our ability to make more accurate measurements.
And really in those marginal areas where salinity becomes a bigger factor and you're trying to look at the actual pore water electrical conductivity, which we'll come back to later, that's where this increased performance is really going to shine in the Solix 14.
This next question is asking if we will benefit more from the Teros 12's verification clip workflow or the Solix 14's onboard diagnostics.
Ooh, I'm so glad we went there because interestingly enough, the sensor has the verification clip built into every reading.
Yeah.
Which is awesome. You know how often as a support scientist, I was asked, well, the water content of my sensor hasn't changed, or I don't trust the sensor because the reading hasn't changed. And to know the answer to that, 90% of the time, 98% of the time, some made up percentage of the time, that was almost all the time, the sensor's working just fine. And you can either be patient until you get some precip, or, let the water infiltrate just a little bit further. Or you could dig up the sensor, put it in air, test it in a bucket of water, or the verification clip, which is the best, find out, okay, yes, the sensor is working. Now I got to put this sensor 6 feet back into the ground. Well, now every single reading of the Solix 14 has a QA/QC check on it.
Yeah.
Leo, how does that work?
Yeah, it's a great question. I mean, let's start with why we did this. And that was, we always have the question of how can I trust that the electronics are working? And, as you've dealt with this for years, the verification clip was a great step in the next direction to instill confidence.
It was so helpful.
Yeah. And then the next question was, well, how can we do this in the sensor? And that was what you asked.
Yeah.
So how can you do this in the sensor? And at first, it was like, that might not be possible. It turns out it was. And Paolo went back and did some amazing stuff to redesign the circuitry. And he came up with a way to build it into the sensor where we're looking at the reference components and essentially doing some really neat math to validate that the reference components are each reading as they're supposed to.
And they're checking one against the other.
Exactly.
So if something goes wrong in the circuitry, then that will shift, and it's kind of an analytical algorithm to check against each other.
Yeah. And so I think being able to build that directly into the sensor really, don't get me wrong, I love the verification clip was a great step in improving confidence in the sensor, but being able to build it directly into the sensor, now we don't have to pull the sensor out to feel
6 feet
that it's
is
reading,
a
right?
big hole to dig just to see if your sensor is functioning.
And odds are you're going to damage your sensor when you pull it back
or
out.
the cable, and just nobody wants to spend their afternoon doing that.
No, I don't advise anybody to do that. And so, build it into the measurement, gives us confidence that the measurement is working with every measurement that it takes.
And now you have an onboard QA/QC.
Exactly. So I'm really excited with that addition and that new piece that was built into the technology.
Me too.
Hopefully it will ease some pain.
All right, with that background, let's get into a few questions exploring why CDX matters in different situations. So the first question here is asking, just in general, how much does salinity affect traditional soil moisture sensors?
Yeah. That's a great question. I think it really depends sensor type or technology for one thing.
This is true.
Yeah.
So they're all going to be a little bit different.
Yeah.
Let's talk about the Teros.
Yeah.
Because we have a lot of experience with that. And for example, like your water content measurement in any of our Teros line will basically start to get kind of iffy, and you'll see the water content reading affected by the salinity at saturation extract ECs greater than 10 decisiemens per meter. And this is pretty consistent across the Teros 10, 11, and 12.
Yep.
And so basically what's happening is that the water content measurement is pretty robust to salinity. It is factored into the calibration at the lower ECs, but once you cross that threshold, it really starts to affect the water content reading.
Yeah. And some of that has to do with the frequency that we operate at 70 megahertz and things like that. And so to a point, we kind of mitigate some of those effects until you get up to that 10 decisiemens per meter saturated extract EC. And that threshold changes for different technologies, but ultimately what happens is when you get into those conditions, you start to typically overpredict your water contents, and so you typically, that means you're going to have to build custom calibrations if you want to use those sensors in those
to
conditions.
a point.
Yeah.
But there's lots of challenges with that as well.
Because the EC changes.
Yeah. And at some point, you get too much salt in the system, too high of an electrical conductivity for a custom calibration to even help.
Right. Yeah. It limits the range that the sensor can actually operate in to actually make good measurements. So.
Okay, so explain then why CDX is better in saline soils.
I mean, I think it comes back down to what we talked about, our ability to separate the imaginary and the real portion of the dielectric and focus in and hone in on that real portion measurement helps improve the range that we can make good measurements into. And it minimizes the effects across a range of ECs.
And it basically accounts for that EC effect on the dielectric of the material.
Yeah. Yeah. And so it's just knowing that we're trying to build for this, being able to build the tools to actually account for that, separate out those things, just helps make better measurements.
Okay, so does CDX only matter then in high salinity conditions, or does it help in normal soils as well?
I would say certainly doesn't just help in high salinity conditions. Even in lower salinity conditions, especially when we're looking at things like trying to measure pore water EC, this improvement in our ability to estimate dielectric permittivity improves our ability to estimate pore water EC using models like the Hill-Horst equation.
For the electrical conductivity, I agree.
Yeah.
For the water content, I'm going to push back a little bit since it's still, since that's calibration dependent.
Yep.
Basically, the underlying assumption is that you have one function to convert that real versus that real or apparent dielectric to give you an accurate water content measurement in all soils on the planet Earth. There's a lot of variability in soils, and I don't think that's a reasonable expectation. Right. And if you have a consistent capacitance measurement and so that you get low probe to probe variability, and that you have a calibration that encompasses as much of that soil variability as possible, then like the Taros line, you can make a sensor to reliably measure water content across a lot of different soil types. But it's not reasonable to expect it to capture all of them. And even so, I think it's kind of a similar challenge in water content for the Solix 14. It's got a great measurement of the real dielectric, but again, there's so much variability in that conversion from dielectric to water content that the calibration kind of becomes the limiting factor.
Yeah. And I think that's a great point to hit on that. You know, CDX is a great technology, but it's not going to eliminate everything.
What I'm trying to say is don't feel the need to go out and replace all of your Taros probes or your TDR probes if they're giving you the good data in the soils that you have.
Yeah, no, I think it's a great point. And I mean, that's what we see in normal conditions, you're going to get good measurements from the traditional tools and the new tools. It's just when you're getting into these things where you're trying to do some of these specialty cases, whether it's estimating better pore water EC or trying to make better measurements in high salinity conditions, or even in some of these areas where you maybe have some of those lossy clays that could potentially cause some challenges. I mean, there are areas where it can help make some improvements, but the traditional tech is going to perform well in most normal conditions.
By normal, we mean relatively low EC conditions and a soil type that fits somewhere within the normal soil texture classes.
Yeah.
And beware of heavy clays as always.
Heavy clays and weird mineralogy, iron-rich soils can be challenging too, things like that.
Okay, so you mentioned talking about soil-specific calibrations. Does the CDX then reduce the need for those, I guess, soil-specific calibrations?
Reduce maybe in EC situations.
In EC situations, yes. Yeah.
As we mentioned in... if you hit high organic matter contents, I would expect those to be a little bit different than the assumptions in the Solix calibration. Volcanic soils are always weird, high iron content soils. There's still going to be situations where you need soil specific calibrations in the Solix.
Yeah. And when you think of our dielectric mixing model, what we're actually taking into account when we're making those measurements, it's taking into account those things, the mineralogy of the soil, and we build and the airspace and the water and all of some of these other things. When we build our calibrations, we try and build a calibration set that covers the range of soil types. And so that gives us where even with the best technology, we still fit within that plus or minus 3% accuracy. If you need better accuracy for your measurements, then do a soil specific calibration. Because again, you're taking something that's meant to cover a range of soil types and trying to apply it to a very tight thing. And so if you want that plus or minus 1% accuracy, you're going to need a soil specific calibration.
Now tell me more about that. This is really what interests me, as like some of the things that interest me as a scientist, and the dielectric mixing model. So for our taro sensors, and we've mostly always done this, is for the taros, there is an empirical calibration, right? Yep. That is just the best fit, the best observed fit from the observed output for the taros to the known water content, observed gravimetrically. And then we fit that best fit relationship and, voila. But it's not really, that relationship doesn't mean anything, right?
Right.
But this dielectric mixing model in the Solix, is that straight up? Is there any empirical fit to that? Or is it just straight up the dielectric, what the theoretical mixing model should be?
Yeah, I know that's a great question. I mean, so what we're still doing is we are taking a library of soils and making measurements to create a calibration now from just dielectric permittivity to water content. But you were talking about a library of soils that range from a sand to a sandy loam to a silt loam to a clay. And within those soils, you have different components of it that impact what that dielectric permittivity looks like. For example, the sand is going to have a slightly different dry dielectric permittivity than the clay and the silt loam. And so we're trying to take all of that into account in this singular calibration equation. And it works pretty well across a range of conditions. But when you get into those specific soil types, because we're building all of that into that calibration equation, of course, it's not going to perform 100% perfectly in one set condition. We're trying to build something that covers a range of conditions.
Okay.
Do I think soil-specific calibrations are useful? Always, if we need to improve our accuracy. Do I think everyone needs to do them? Absolutely not, because they're a lot of work.
At what point does salinity still become a challenge even for CDX?
I haven't found that limit yet.
Yeah, we haven't found it yet. We're exploring that right now.
I was really excited when you were showing some data that had added water to the soil so the solution was 50 decisiemens per meter.
Yep.
So at saturation, that saturation extract was 50 decisiemens per meter.
Exactly.
That's close to seawater.
Yeah.
That's crazy.
Yeah, those are super high levels, and from what we can tell, the measurements still performed well. So.
And that it looked, if I remember correctly, it just followed the same trend line as 30 decisiemens, the 10 decisiemens.
Yeah.
You couldn't even distinguish between those data points.
Yeah.
That opens up possibilities for estuarine research, really compromised site, salt flats.
Mining applications.
Yeah. Wow.
Yeah. Yeah. I mean, every measurement has a limit. We are working on exploring the limits of this technology. We're going to do a webinar on this here in the coming future. And if you're watching this later on down the road, you may find it's already been run. But we're continuing to explore the limitations of the technology, but it really does seem to have opened up the range of what we can work within. It's pretty exciting.
That's awesome.
So does CDX then improve pore water EC estimation?
Chambers?
Yes. From what I've seen, it's really, really, we still have some more testing to do on that, right? But
for sure.
especially over previous attempts that, well, let's unpack this a little bit. Why would we expect the Solix 14 to improve the pore water EC measurement?
It's a great question. Well, let's start with using the Hill-Horst equation, for example.
Exactly, right.
What is some of the primary inputs into the Hill-Horst equation?
Dielectric.
Dielectric, and it's the real dielectric.
This is a real dielectric.
Specifically.
Yep.
So if we're using apparent dielectric permittivity measurements to estimate pore water EC, the apparent dielectric permittivity is potentially affected by salts.
And temperature.
And therefore, it is going to cause an inaccuracy in your estimates of your dielectric permittivity, which then compound into errors in your estimates of pore water EC.
Right. And where we're measuring the real dielectric very, very accurately in the Solix 14, then where something like the Terros 12, especially at low water contents, the Terros 12 data would be really iffy.
Yep.
Just because the signal to noise ratio got so small as that the noise from the uncertainty in the dielectric measurement got larger.
Yep.
At low water contents, the Terros 12 would kind of give you an idea of where the pore water ECs, but wouldn't really be reliable.
Yep.
Whereas the Solix 14 is even down to like 4 or 5% volumetric water content. From what I've seen, those pore water ECs are looking really good.
Yeah. Yeah. So, any improvement we can make in our estimates of the actual dielectric permittivity are going to make improvements on our ability to estimate pore water EC. And we're really seeing the impact of that from this new measurement.
Because that's what people really want to know, right? The bulk EC doesn't really tell you anything about what's happening in the plants. You want to be able to look into that soil and see how the electrical conductivity of what's in your soil is changing because of the solute concentrations, right?
Yeah.
You don't want to be confounded by changes in water content or changes in temperature.
Yep.
So being able to separate what is changing in your soil because of the fertilizers you add without having to worry about the water content is what we really want.
Yeah. Yeah. And this is really going to open up our ability to do things like salt balance estimates.
Salt balance.
Understand how water is moving through the soil profile. We think of this in such a small frame, but I think this is really going to improve our understanding of so many different things in soil.
Okay, we will move on to some questions about field use and installation. And this first one is asking, is installation still critical for accuracy even with CDX?
Yes.
Always.
Installation for a sensor that measures the electrical properties of the soil to get at water content or EC. Getting good contact with the soil is going to be just as critical in the Solix 14 as in any other sensor.
Yeah. I mean, maybe unfortunately, but with this, any type of this measurement tech, we need good soil contact. We need to minimize air gaps. And honestly, we also want to minimize site disturbance. And so and we've said this, I can't count how many times we've said this, but regardless of how good your sensor is, if your installation isn't good, you're not going to get good measurements. And that doesn't change with the CDX tech. It doesn't change with anything.
Yep, that's right.
So does CDX with the Solix 14 require any kind of different installation practices than our Terros sensors?
No. Use the same things, use the same considerations. It works with the Terros borehole installation tool, which is highly recommended, especially in deeper installations. And rule number 1 is make sure you get good contact with the soil, between the soil and the pins.
Yep. If all else, remember rule number 1. But, when we set about designing the CDX and the Solix 14 sensor specifically, we had a couple goals. One of the goals is that it worked with the borehole installation tool because we know the power of the borehole installation tool in getting good installations, especially at depth, and minimizing site disturbance. And so we designed it that it's going to work similarly with those tools. And so you're nothing really changes there. I think the only other thing that really does change is we've made this sensor a little more robust. And so it just kind of helps improve our ability to install the sensors without damaging things. Doesn't mean you should get reckless with it, but it is
still watch out for rocks.
Yeah, watch out for rocks. Rocks are going to be a challenge always. And but yeah, for the most part, the same principles that apply to the Terros 12 or the Teros line of sensors are going to apply to the Solix 14 when it comes to installation.
So if I'm installing both Teros 12 and Solix 14 sensors in the field, how could I best compare the measurements that are coming from both those sensors?
Custom calibration.
You can do a custom calibration. I mean, the one thing to remember is that both of these sensors, the library of soils that we use to develop our calibration is the same library. And if you're measuring in normal soil conditions, like we talked about, low UC, and typical mineralogy, they
Normal
should.
soils.
What is the definition
Every
of normal?
soil is normal.
But from what we see is that comparing these sensors, they compare fairly well. If you're getting into situations where you're outside of those ranges, soil-specific calibration is going to help where you can do better cross comparisons. And if all else fails, follow the guidelines that we're putting together as a part of the National Soil Moisture Network, which is install sensors where they overlap for a period of time. So you can do intercomparisons while they overlap and see how they're performing against each other. But I think in many cases, you should be able to do comparisons in most conditions. But if not, soil-specific calibrations are great.
And do bear in mind that even if it's a fairly typical soil, there's uncertainty around the measurements. They both rely on a relationship over several points from the electrical properties to the water content. And so anytime you get an uncertainty like that, a particular soil might fit high for one sensor and low for the next sensor. Both sensors are working perfectly well and you have a 5% difference. It's just part of the reality when you're comparing different types of sensors. And in that case, do a custom calibration.
Yeah. And we can't ever throw out just the fact that there is also spatial variability. Even when you have these sensors installed in a site close to each other, it's also possible that the water content just naturally varies from point to point. We know that this happens. So you have to remember that too when doing comparisons in the field.
Okay, that's going to wrap it up for us. Thank you again for joining us today, and we hope that you enjoyed the discussion. And thank you again for all the great questions. And again, if you have any questions that we didn't answer, please contact us via our website at metergroup.com. Finally, subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. Thanks again, stay safe, and have a great day.